I think it will be done in a couple of classes, and after that we have just one chapter remaining, chapter 16. It's about time series analysis, yeah, which is quite different from typical regression analysis. Yeah. So to end the finishing touch to this regression analysis discussion, we have to talk about a couple of things. Yeah. The first thing is collinearity or multi-collinearity. Yeah? I think more frequently we call it multi-collinearity. Multi-collinearity. Yeah? Multi-collinearity is a very important concept. I hope you will get good understanding of this concept. Okay? This refers to the situation where two or more independent variables are highly correlated. Okay? You know the correlation, right? Correlation, we talked about correlation coefficient R. And if you say Rxy, okay, is say 0.85, something like that, right? Let me make it simple, 0.8. What can you say? Correlation coefficient is 0.8 between x and y. And let's say we're talking about y, x here. And suppose you ran a regression, y is b0 plus b1x, right? Can you say anything based on this? I'm sorry, what? Positive relationship, right? Well, are you absolutely sure? Very right, very good, right? Yeah, so let me just try to refresh your memory, right? Correlation coefficient would be somewhere between -1 and 1, right? And by looking at the sign and magnitude of the correlation coefficient, you can get the idea about the direction of the relationship between the two variables, and also the strength of the relationship between the two variables, right? So if it's 0.8, what it indicates is, well, we may have some positive correlation, and you can say the relationship is relatively strong. Right? Positive linear correlation is relatively strong, right? Can you say anything else? Anything more than that? What about the regression model here? Will it be useful? How can you say? If R is 0.8, huh? Yeah, of course, right? That means R square is what? 0.64, right? So, what can you say? Yeah. Okay, about 64% of total variation in y variable, right? So we have this the variation in y values, right? And out of the total variation in y values, about 64% is explained by the x variable, right? The variation in x variable. Or you can simply say about 64% of the total variation in the dependent variable is explained by the regression line, something like that, right? Yeah. So, yeah, that's what we're talking about, the correlation coefficient, right? Well, we're talking about multiple regression right now, and let's say x1, x2, xk. Yeah? You have multiple independent variables, okay? And multicollinearity refers to the situation that some of these independent variables have high correlation, right? So R x1, x2 tends to be high, either negatively or positively, right? So the absolute value of our correlation coefficient comes close to 1, right? Then it is a problem, right? Well, the high correlation between independent variable and the dependent variable is good because that will increase R squared, right? And that means our regression model will be useful, more useful, right? So based on the x value, if we make a prediction on y value, there's a high probability that it will be accurate, right? So we would like to have high correlation between x and y, right? And in multiple regression situation, we'd like to have high correlation between x1 and y, x2 and y, and so on, right? But high correlation between independent variables will cause some problem. Okay? Well, exactly what problem, right? Well, redundant information, first of all, right? If x1 and x2 are highly correlated, right, that means two variables provide redundant information. Okay? So, we have y, x1, x2, xk, okay? And we have all these observations, right? But suppose the correlation between an x1 and x2 is something like 0.9, right? 0.9, right? Pretty close to 1, right? What that means is anytime x increases, x1 increases, x2 also increases, right? Anytime x1 goes down, x2 also goes down, right? There's a high tendency, very strong tendency that the two variables change together, right? Then what that means is x1 and x2 are providing redundant information, the same information. So what that means is one of the two is useless, right? If they provide the same information, you don't need the two, both independent variable, right? So, when we estimate this model, we would get y hat is beta b1 plus b0 plus b1 x1 plus b2 x2 plus bk xk, right? And how do we interpret this coefficient? What's the typical interpretation of that slope coefficient estimate? How do we start if you want to interpret that B coefficient? Okay. For 1 unit increase in x1, y increases by b1. Is that it? Holding other things constant. right? In other words, holding x2 and other independent variables constant, this is the impact of x1 on y, right? That's the typical interpretation, right? But if x1 and x2 change together, can you hold x2 constant while x1 increases? No, right? So we got a problem here, right? So the estimate of this coefficient will not be accurate because that's what the computer does, right? When you have multiple observations, right? Computer looks for the okay, between this observation and this observation, x1 increased by certain amount, right? And so there should be some variability, the difference between x1 and x2, right? So that, okay, well, so between this one and this one, x2 did not change that much, x1 changed quite a lot, right? And as a result, y increased by a certain amount or decreased by a certain amount, right? So by comparing that, computer figures out, or mathematically, right, this equation figures out the effect of x1 on y, right? That's how B1 is calculated, right? But anytime x1 increases by 1 unit, x2 also increases by 1 unit, right? Then there is no way we can figure out B1 mathematically, right? Does it make sense, right? So that's the situation we're referring to. The estimation will be difficult or impossible, right? And the interpretation will be quite messy, right? It's not going to work exactly, right? So we're going to talk about the symptom in the next slide, okay? But here, it can lead to unstable coefficient. It can lead to unstable coefficient, and coefficient signs, estimated coefficient signs may not match prior expectations, right? So one typical result of this high correlation is independent variables turn out to be insignificant, right? Why? Because if x1 and x2 provide redundant information, right, then the situation is x1 is insignificant in the presence of x2. x1 is insignificant in the presence of x2, right? Because x1 and x2 provide the same information, right? Because we have x2, you don't really need x1, right? So the parameter estimate, when you get this parameter estimate table, right, the t values tend to be small and p values tend to be large, which means the independent variables are insignificant. Okay? So that's the idea. Vice versa, x2 will also come out to be insignificant because x2 is insignificant in the presence of x1, right? Because you have x1 and x1, x2 provide pretty much the same information, you don't really need x2, right? So in the simple example, let's say you have only two independent variables, right? Y is up to this part. Suppose this is your model, cannot reject the null hypothesis, right? Beta 1 is 0, beta 1 is not 0, right? and beta 2 is 0, beta 2 is not equal to 0, right? In both tests, right, you won't be able to reject the null hypothesis, right? And that means you'll conclude that, well, we don't have sufficient evidence to reject the null hypothesis, right? Here or here. So you have two independent variables. Your conclusion is both independent variables are insignificant. And yet, if you look at the F-test here, right? F-test turns out beta 1 is beta 2 is equal to 0. At least one beta is not equal to 0, right? And here you have sufficient evidence to reject the null hypothesis. You came out to be insignificant. Your conclusion was both x1 and x2 are insignificant, right? But somehow, when you test the entire model, your conclusion is model is useful. Does it make sense? Yeah? Doesn't make sense, right? The thing is, that's the very, very typical, very interesting, important symptom of multicollinearity, right? Individual coefficients turn out to be insignificant. Individual independent variable turn out to be insignificant, and yet entire model turn out to be either x1 or x2 or both are important. Let me repeat again, right? In fact, in reality, either x1 or x2 or perhaps both provide useful information in predicting y value, right? So when you test the entire model, you reject the null hypothesis, right? However, when you test the individual parameters, beta 1, beta 2, right? Because of this, yeah, computer finds out, well, x1 and x2 change together. So because x2, in the presence of x2, x1 is really unnecessary, right? And then when you test x2, says, well, because we have x1, which provides pretty much the same information, x2 is really unnecessary, right? So both independent variables turn out to be insignificant, right? Well, so the point is, if you have multicollinearity, pretty much these estimates for individual beta parameters, beta coefficients, right, become unreliable, inaccurate, and unreliable, right? Because of this confusion. Basically, computer is confused, okay? Because x1 and x2 are providing pretty much the same information. You can't tell which unusual signs. Let's say you estimated wage equation, wage earning as a function of schooling, experience, and so on, right? And typically you would expect positive sign for schooling, right? Because as someone acquires higher level of schooling, the person's wage earning should be higher. Typically, as a person acquires more and more experience in the labor market, the person's wage earning would increase, right? But somehow your estimation comes out to be negative, right? Then you should suspect some multicollinearity problem, right? So some of these independent variables are highly correlated, or the schooling is highly correlated with some other variable, right? And that's causing some problem, right? Confusion, right? Large change in the value of previous coefficient when a new variable is added to the model, right? So when you add a new variable, suddenly the estimate of existing variable coefficient, right, changes dramatically, right? It used to be positive, suddenly become negative, right? Or there's a huge change in the size of the coefficient, right? Then you should suspect some multicollinearity problem. Yeah? A previously significant variable becomes non-significant when a new independent variable is added, right? The same situation. Estimate of the standard deviation of the model increases when a variable is added to the model, right? Standard deviation of the model, what is it? Standard deviation of the model. What do we call that? Standard deviation of the model. How do we write S? Standard deviation of the model. What are we talking about? Huh? Again, I apologize, all these things are in Korean language, okay? But by now you should know what these are, right? In your German or Italian or whatever, right? Okay? All right. So, standard deviation of the model refers to S, Y, X, or we can say standard error of the estimate. Typical reference is standard error of estimate. That's here, 표준 오차, that's standard deviation, right? This is SYX, okay? And this is actually the square root of here. I'm sorry, what is it? What is it? SSE? Yeah. This is SSE, right? Oh, here. MSE, sorry. MSE, mean square error. Okay, so if you take a square root of this, you get this. So this that's RMSE, root mean square error, that's SYX, root mean square error. How do we correct? How do we prevent this problem? Okay? Well, we have to figure out which one is causing the problem, and we have to eliminate those variables. Okay? So how do we eliminate? The first step is you have to look at the correlation table. Okay? Before you run the regression, actually, this is a good practice. Before you run any regression, you have to look at the correlation table among independent variables. Okay? So what we're talking about is this. E1 is actually midterm exam. I say E1 here because I used to give 2 midterm exams. Okay? So 2 midterm exams and the final exam, so it goes E1, E2, and the final exam. These days I give only 1 midterm exam, right? So this is the midterm exam, this is the final exam, absence, participation, and this is final average, which is calculated based on these 6 independent variables. Okay? So if you're going to use these 6 independent variables as independent, 6 variables, okay, go to data analysis, and there should be, okay, all right, go to that, and then you highlight the whole, all the independent variables, include the label. Okay, and direction of data, you have to tell the computer that which one is the variable, either is it row-wise or column-wise, right? Well, we have, you want your output, okay? Let's say I want it here. I think that's it. Let's see. Right, okay? And you got this correlation coefficient among 6 independent. So computer gives us only 1/2 of the table, right? And in the diagonal here, they are all 1. It's an absolute value, right? So either 0.8 or above, or negative 0.8 or below, right? That will be a problem, right? That's this kind of eyeball method, right? This is only a first step before you run the regression, right? Have multi-collinearity problem, right? That is VIF, variance inflationary factor, eh? Proposal or whatever, right? Then you usually include this VIF measurements, right? To see